Okay, we're on lesson 40, unit 7, page 448, double angle and half angle identities. We dealt with sum and difference identities. And the reason we're doing these things like sum, difference, double angle, half angle, is we've memorized 30, 45, 60, those angles, right? 90, and then the quadrantal angles. Well, if something's not 30, 45, 60, or a quadrantal angle, we really don't have that memorized or know how to deal with it without going to the calculator and punching it in and getting some rounded answer. If we're in search of exact answers, then we need to go back to those memorized 30, 60, 45, 90 numbers. And so that's what we're going to try to do even with the double and half angle identities. If you looked at sine 45, you might think, well, how could I get, sine 75, like number 7 down here at the bottom left of the screen, which is number 7 on your worksheet. You would say, well, how could I get 75 with a plus or a minus? Well, you might say, well, that's 30 plus 45. We could do it with a 30 plus 45. So we could use a sign of a sum and actually do this one. It could be, though, that you can't hardly split it into the sum of two nice, pretty things, and so you might want to think of it as half of something you know how to deal with, or double something you know how to deal with. If you had, for instance, the sine of 15 degrees, that's not memorized, but we know that that would be the same as the sine of 30 degrees divided by 2. So we could apply a half angle identity, okay? Or we might say, well, let's say that I had even here with the 75. 75 is half of a number that has a reference angle of a pretty number, okay? So let's just look at that. I haven't even talked about the rules at the top yet, but let's just look at number 7, and then we'll go to the rules at the top. 75 is half of what number? 150. So if we thought of this as the sine of 150 divided by 2, then we got something we kind of can understand. 150 degrees has a reference of what? It has a reference of 30. If we go back into our memory work, 150 degrees would be from here to here. That's 30 degrees from the x-axis there. And so 150 has a reference of 30. So if we thought of 75 as half of 150, 150 having a reference of 30, then we're back to an angle that we know how to deal with. What we do then is just expand this according to the expansion rules that you see at the top. Now, at the top we have the double angle identity. Sine of 2 times some angle is 2 sine A cosine A. The cosine of 2 times some angle, you have 3 options: cosine square A minus sine square A, 2 cosine square A minus 1, or 1 minus 2 sine square A. And this is where we're actually going to use our sheet and look back and forth. You probably figured out from the last test, though, if you didn't do a lot of memorizing, the sheet was kind of hard to use, because as you're trying to verify identities, it needs to just hit you that there's something that looks like such and such. Or you spend all this time trying to figure it out, and it's just not going to click in your mind. So memorizing these is better than having a sheet to look at, or at least having a pretty good familiarity with them. The tangent of 2a then is 2 tangent a over 1 minus tangent a. And then we have our half angle identities. We have sine of some angle divided by 2 is plus or minus square root 1 minus cosine a over 2. The cosine of some angle divided by 2 is plus or minus the square root of 1 plus cosine a over 2. The tangent of a over 2, we have 2 choices: 1 minus cosine a over sine a, or sine a over 1 plus cosine a. Now, what we're dealing with here in this situation is the sine of some angle divided by 2. So we're going to use the sine of some angle divided by 2 rule right there. And so we're going to have plus or minus the square root of 1 minus the cosine of that angle, 150 degrees, the angle that got divided by 2, over 2. Everybody see how we got that? So we thought of 75 as being half of 50, half of 150. And so then we went to the sine of half of an angle, a divided by 2. The 150 was the a. So then we have plus or minus 1 minus cosine a over 2, the a being the 150. Understand that? Now, what we can do here is figure out what the cosine of 150 is. Now, we're in quadrant 2. This is a smart trig class, right? They're all positive in quadrant 1. Sine is positive in quadrant 2. Tangent is positive in quadrant 3. Cosine is positive in quadrant 4. We're really talking about 75 degrees, right? We were to start with. Presently, we're talking about 150. The reference angle for 150 is 30. What is the cosine of 30? Square root 3 over 2. So we're going to have plus or minus the square root of 1 minus square root 3 over 2 over 2. Now, but we got to talk about the sine. Cosine of 150, we're in quadrant what? We're in quadrant 2, where cosine is negative. My formula had a minus, but it's a negative, and minus a negative is a plus, so that turns into plus or minus the square root of 1 plus square root 3 over 2 over 2. Now what we have is a complex fraction underneath the radical, and we want to try to simplify this as much as we can, okay? Okay, so what do we not like about this most at this present time? We don't like the fact that it is a complex fraction. We don't like that denominator. Now, we could reciprocate and multiply, or we could, at this point, just say, I want to get rid of that complex fraction situation, and I'm going to do that by multiplying the numerator and denominator by the denominator I don't like. I'm going to multiply the numerator and denominator by the numerator's denominator. That sounds kind of weird, I know. But anyway, so we're going to get plus or minus square root of. Now this is going to distribute, right? 2. And then this 2 is going to cancel the 2 on bottom. And we're going to get square root 3. So 2 plus square root 3 over 2 times 2 on the bottom is 4. Now that's all still under that big old square root thing, right? So we have plus or minus square root of 2 plus square root 3 over 4. I heard that question. I'll answer that in a second. There was a question, can you do something with this 2 and 4? You cannot unless you distribute it here, right? Because if you were going to divide the 2 by 4, you would also have to divide the square root 3 by 4. But it doesn't have a coefficient that would reduce, so you can't just reduce one piece. So we can't mess with that. But let me just show you what that's like. This is like square root 2 plus square root 3 divided by square root 4. Let's just go ahead and rewrite it like this, plus or minus. That, remember when there's a fraction in a radical, you split it apart? Radical of numerator over radical of denominator, okay? And then what is the square root of 4? 2. So we get plus or minus the square root of 2 plus the square root of 3 over 2. Okay? Now, it's positive or negative, but it's not both. Because we got to go back to the original. The original was sine 75. What quadrant is that in? 1, where everything is positive. So we're going to take away the minus part of that and just make it a positive 2 plus positive square root of 2 plus square root 3 all over 2. It ended up being positive because it was in quadrant 1. Let's see how we got that. Wow. Okay. Any questions there? Is anybody still writing? Okay. All right, number 8. Number 8, we have tangent 22.5. Now this one, we couldn't hardly do a sum or difference. This one just isn't going to work in a sum or difference. We've got a decimal in it. But what could we think of that as having been a half of? 45. So we're going to rethink that as the tangent of 45 divided by 2. Which means that we can apply our half angle identity for tangent, right? And so that's going to be equal to 1 minus cosine A over sine A, A being 45, right? So 1 minus cosine 45 over sine 45. 1 minus cosine of the angle A, which was 45, over sine of that angle A, which was 45. And we know how to find sine and cosine of 45. Okay? Any questions there? So, what is this cosine of 45? Square root 2 over 2. So we're going to have 1 minus square root 2 over 2 over, what's sine 45? Square root 2 over 2. So we have a complex fraction. What do we not like? The complex fraction. We want to get rid of the denominators of the numerator and denominator, and we do so by multiplying the numerator and denominator by the common denominator between the denominator of the numerator and the denominator of the denominator. So we are going to distribute. So 2 times 1 is 2. And then the 2 would cancel here, and we get a minus square root 2 on top. On the bottom, the 2's are going to cancel, and we're going to get a square root 2. So we have 2 minus square root 2 over square root 2. So it looks better. It's not a complex fraction. It's just a plain old fraction. But you cannot have a radical in the denominator of a fraction. So we rationalize by multiplying it by square root 2. On top, it has to distribute. Square root 2 times 2 is 2 square root 2 minus square root 2 times square root 2 is plain old 2. When you multiply a square root by itself, you get the radicand. On the bottom, square root 2 times square root 2 is plain old 2. Now what you see is that the denominator 2 will divide evenly into both the numerator and denominator. And so we're going to apply the distributive property. And when you do, you would get square root 2 minus 1 which could be written as negative 1 plus square root 2 if you want to write the radical second. So square root 2 minus 1, or a different form, negative 1 plus square root 2. Any questions on number 8? So you see that what we begin with is to think about how to half or double. We simply stick it into the appropriate formula, and then it becomes an algebra problem, messing with complex fractions and messing with radicals, okay? Which are things that we should have had in our past from algebra, college algebra, at least. Those is pre-calculus, but the whole first semester we did college algebra, so we should have that under control. Any questions on number 8? Okay, so we got some half-angle identity stuff. We'll look at some double-angle identity stuff. So, number 9. Number 9. Running a little slow there. Okay. It says that cosine theta is equal to 4 over 5 where 0 is less than theta is less than 90. And what we want to do is find sine 2 theta. Now, first of all, the sine 2 theta will expand using this equation, right? So sine 2 theta is going to become 2 sine theta cosine theta. We already know what cosine theta is. So this is going to become 2 times whatever sine theta is times whatever cosine theta is, and cosine theta is 4/5. All we lack to be able to solve is to find out what sine theta is. We already knew what cosine theta was. And that gets back to our XYR stuff, right? Now let's go through these again. Some of us may remember and some of us may not remember. I'm going to put it right under the recorder. The sine of theta is what over what? Y over R. Cosine of theta is X over R. And tangent of theta is Y over X. Those need to be memorized. Sine is Y over R, cosine X over R, and tangent X over Y. Based on that information then, we know that cosine theta is equal to X over R. That means my X is 4 and my R is 5. And I can use the Pythagorean theorem to get my Y. X squared plus Y squared equal R squared. So X, which is 4 squared, plus Y, which we don't know square, is equal to R, which is 5 squared. We're going to do the squares. Get the junk off of the Y square, so we're going to subtract 16, the junk off of Y. And so we would have Y squared is equal to 9. We're going to take the square root, and we're going to get Y equal 3. Now, we could say plus or minus 3, but we're talking about distance, and there's no such thing as a negative distance. We're not going to deal with negatives when we're doing the Pythagorean theorem here. We'll deal with negatives when we think about what quadrant it's in, right? Now, why did we get that Y? Because we know that sine is Y over R, which means that sine would be my Y, which is 3, over my R, which is 5. So sine Y is 3 over 5, which I needed to put right here. Sine theta is 3 over 5. So we took sine 2 theta, we expanded it. We already knew cosine theta. We didn't know sine, so we did the Pythagorean theorem to get y. Sine is the y over the r, which is 3 over 5, and so now we just solve. This is like 2 over 1. 2 times 3 is 6 times 4 is 24. Over 1 times 5 is 5 times 5 is 25. And so we get 24 fifths. Any questions on number 9? So we evaluated 2 pi. Now we need to check our signs. We're talking about the sine of some angle. We need to know where it's located. That's going to determine the sine. Where does it tell us it's located? Between 0 and 90, meaning that it's in quadrant 1, which means sine is positive, so it's a positive 24 25ths. Yes. Yeah, we found the value of sine 2 theta. See, thank you. Thank you. The the statement was, we're talking about sine 2 theta, and we want the answer to sine 2 theta. Theta is in quadrant 1. So where is 2 theta? Now that could become a challenge, because if theta was actually 30 degrees, double that would be 60. If theta was 20, double that would be 40. If theta is 45, it becomes 90. So it's going to be hard to determine, if we don't know theta, where 2 theta is at. Did it end up in quadrant 1 or 2? So how could we figure that out? That's correct. The good news is, in quadrant 1, they're all positive. In quadrant 2, sine is positive. So if we're looking for sine, it's not going to matter if it landed in quadrant 1 or 2. But if it had been cosine, it could have been a problem. Or tangent, it could have been a problem. Could we actually find the angle? Yeah, we could do inverse cosine, right? And we could get an angle measure. If it was cosine or tangent, we could do arc cosine, and we could actually get an angle measure that went with that 4/5 and tell what that angle was, and using that we could double it and see if we landed in 1 or 2. But yeah, but since it said sine, we're off the hook. You're right. Very good. Thank you. Any other questions or thoughts? Good stuff. A lot of stuff involved here. All right. Good stuff. All right, number 10. I'm kind of getting into some of my rules here, chopping into my... Okay, let me see if I can clean it up without making a mess. I know when you're watching the videos, this is kind of gets a little boring when I'm cleaning house. But anyway, number 10, not that anything I ever did would remotely have the chance of being boring, but anyway, cotangent of theta is equal to 3 over 2. And it says we're talking about 180 less than 0 less than 270, which means quadrant 3, right? Which means quadrant 3. Oh. Yeah. Yeah, which means it's in quadrant 3. And we're looking for sine 2 theta again. So we're going to expand the sine 2 theta again using that. And we're going to have 2 sine theta cosine theta. 2 sine theta cosine theta expanded. We know cotangent theta. We know that cotangent is what over what? It's cosine over sine, which is with x's and y's. It's x over y because it's the reciprocal of tangent, right? Tangent is y over x. Cotangent is the reciprocal, so it's x over y. We're going to need to find my radius because sine, remember, I'm just going to go ahead and write this out. This is going to be 2 times sine, which is y over r, times cosine, which is x over r, if that'll help us out a little bit. So we need to find out what the r's are. We already know what x and y are. So we're going to have 2 over 1 times. We know that y is a 2 times. We know that x is a 3. We need to know what r is to get those two denominators for my sine and cosine. We're going to get that r by using the Pythagorean theorem with that information right there. So we're going to have x squared plus y squared equal r squared. So we have 3 squared plus 2 squared equal r squared. 9 plus 4 equal r squared. 13 equal r squared. Take the square root and we get r is equal to square root of 13. So my radius is square root 13, which is going to go here and here. So we're going to get 2 times 2 is 4 times 3 is 12 on top. Square root 13 times square root 13 is 13, the radicand. We're dealing with sine. The original angle was in quadrant 3. If you double it, you could try to figure out where that is going to be. And then try to deal with the sines from there. Again, that's a little challenging to try to think all that stuff out. If you wanted to be exact, then you could do, you'd have to go back to quadrant 3 and see exactly what it was. Somebody do this. How would you type this in to actually find the angle measure? Yes. Actually, no, it's not going to be half of that. The question was, can you just take 12/13 divided by 2? No. We're trying to figure out the angle that would produce that. If we had cotangent of theta is that, then that means that the reciprocal of tangent is what we want, right? So if that means that the tangent of theta is the reciprocal 2 over 3. Buddy, with me there? That means that we could do arc tangent of 2 over 3, and what would you get? Okay, when we did that, we got 33.69, blah, blah, blah. Now, what that tells me is that I'm in quadrant 3, and I'm 33.66 degrees away from there, right? 0.69. Which puts me at 180 plus 33.69, okay? Which is 213.69. Doubled is 427.38. Okay? So if I take that 427.38 and I take out an all the way around, I get 67.38 degrees, which is in quadrant 1, which means that it's positive if you wanted to go to all that extent to figure all that out. We actually could do all that work and know exactly where that was and where double it is, and take out our 360s and play the game till we get where it goes. Okay? Any questions on number 10? We might better stop there. Next time we meet, we'll do number 11 and 12, which is verifying identities, which can be challenging for some. Okay? Appreciate your attention.